This is actually an edited version of a lecture I gave recently. I gave the plenary talk at the Semicon West, which is the world's largest group gathering of people who are sort of experts in the semiconductor area. But I wanted to take it up a couple of levels. And one of the things that IBM has tremendous emphasis on is the impact of what we do on society. And if you've been at this as many years as, or many decades as I have, you do have a concern because we can make huge differences in people's lives, unimaginable, if you just pay attention. It's very easy to ignore the hard stuff, right? The grand challenges. But if you set a challenge for yourself and you set it to be something that will actually change the way the world works, and then you pull it off, and grand challenges don't always work. That's why they call them grand challenges. Albert Einstein disliked intensely the whole concept of doing quantum mechanics. God doesn't play craps with the universe, I believe, is one of the more famous quotes. But the fact is, he pursued a grand unifying field theory through the remainder of his life, attempting to resolve something that he felt would be, seminal, and it didn't work. Of course, his contributions are so extraordinary that his name will never be lost to history. Even though one of the grand challenges he undertook, he was not successful in closing out. That's just how that is. But it is very important when you work in any field, I don't care what field you ultimately go into, that you just keep in the back of your mind there are places where innovation, the big stuff you're going to do, does matter, will have a profound impact, and just keep your eyes open to that because you'd be amazed what you can miss. There are a couple of rather large challenges out there, and I wanted to just set the stage because all of these things ultimately are basically handled, believe it or not, as challenges through information technology in a very large part. Now, in fact, I had a very interesting meeting where before this, in fact, somebody was telling me, gee, I'm going to work on water management as part of my studies in computer science. And I think that's very cool because, in fact, there's a problem here. Right now, if you ask people, will you have a major crisis in water supply, in 36 states where you have folks who own this issue, they say, yeah, in the next 2 years, I will at least once have a major crisis in water supply. Okay, that's way better than half the US. If you look at China, China already suffers, as you well know, from dramatic problems in water supply. And that's not just shortage, but it's also quality. And they're working very, very hard on what's a critical societal issue. India is projected basically to have the world's first there ain't enough water for the population by 2025. And oh, by the way, as you know, the snow caps and in the Himalayas and elsewhere in that area that supply that region are diminishing to the point that you will come to a crisis state. You need to address these things. Traffic. Now this is, prototypically what you find in places like Los Angeles. I don't think I have to tell you where that was. The problem is, right now, if you do quantitative measurements here, people just looking for a parking spot in this one segment, they took a small area of LA and they said, how bad is it? People looking for a parking spot basically drove around the world the equivalent of 38 times searching for a place to put their car. They burned about 47,000 gallons of fuel in the process and put about 700 or so tons of carbon dioxide into the atmosphere. That's not going anywhere. That's just looking for somewhere to put their vehicle. Congested roads in the US right now burn up about $78 billion, according to the best estimates, in terms of just wasted time, lost hours, millions and millions of gallons of fuel burnt. In the US, distributing food, another challenge. And these things, again, if you think about it, if you have IT and you actually have solved the traveling, anybody here heard of the traveling salesman problem? Right, of course, the most efficient way to get to A to Z. Well, the traveling carrot problem, right? A 1,600-mile carrot. You can probably do better, just guessing here. The chuck roast that goes 600 miles, the 1,200-mile potato. I mean, this is amazing. And despite all of the controls we have, you throw out about $48 billion of food a year because it spoils. It just doesn't get to where it's going. And by the way, you should have probably thrown out another $48 billion, but instead you compensate by eating it and then going to the hospital. It's not a good deal. There's a lot of work to be done. Healthcare is another mess. They estimate that about 2.2 million dispensing errors are made because people handwrite their prescriptions. And by the way, if you haven't heard, they're illegible. I think you know that. The healthcare system is estimated to lose $100 billion a year to fraud, and that is a very low ball estimate. That is actually probably very, very conservative. IT can track all these things, and the premise is it's either we lack the information we need to address these kinds of challenges, or we can't utilize it effectively because there is a deluge of it coming at us. And as you know, too much information, if you're fighting a case in law, you know what the first thing you do to the other side to make their life misery? You don't hide anything from them. Hell, you give them everything, including last week's toilet paper. I mean, you just, here it is, boom, and you literally deliver 4 trucks of papers. And somewhere's in there is the one they're looking for. And somewhere's in about 300 years, they will locate this. So what they do is they put 300 lawyers on it for 1 year. And that burns up so much money that the person you're fighting with throws their hands up in the air and says, I quit. It's ridiculous, but that is, again, it's something that happens. Finding that nugget of data is really the most amazing challenge we face. And it is the responsibility of the folks who create the technology to enable us to step up and address these kinds of problems. Technologists, whether you're in the hardware or the software side, are the people who will solve these societal issues. They're not going to solve themselves. This isn't something you're going to wish away. And no amount of work with a shovel or no amount of work with a pencil is going to get this done. We are way past that. Now, the concept of a smarter planet and how, the issues we've been chasing, these are basically what an industry, our industry, in fact, the one certainly I've worked most of my life in, which is in the technology side of this, can enable. And what we decided to do is, because of the unbelievable number of things you can chase, and I'll give you a few examples later, we really focused heavily on the issue of just, how we would work within smarter cities, because they make a great microcosm. Smarter cities are a great place to focus because about 50% of the world's population is going to live there in a matter of years. And about 25% of the entire domestic product of the planet comes from the top 100 cities today. 25% of the world's GDP comes out of just a handful of cities. So again, it was a place we decided to start. Now, in the industry we work in, the technology industry, we actually can make things both economically and technically feasible. This is the first aha. What percentage of the Wi-Fi revolution, right? 802.11, God, you know what 802.11 is, right? A, B, okay. What percentage of the Wi-Fi market do you think IBM was for the first, let's say, 10 years that it started up? Well, approximately. Less than 10%? Less than 30%? Well, you guys are optimists. Less than 50%? All right, let's go the other extreme. 100%? Okay, no votes. 100%. Okay, did anybody even have a clue we were involved? Not a chance. You could make 802.11 Wi-Fi long before we got there. And they sold a couple of hundred a year. Why? They cost $1,000, $2,000 a piece. They were built on gallium arsenide, all kinds of exotic technologies. In the case of the silicon germanium program I led, our goal wasn't to build something that could outperform gallium arsenide. We did, but that was not the goal. The goal was to build something a factor of 1,000 less expensive. Why? Because if you're selling the chips that are required to make Wi-Fi for $1,000, it's never going to happen. The damn computer costs $1,000. I mean, it just isn't going to happen. If you can sell the chips for $10, then you sell 100 million Wi-Fi cards. And we're in all of them. Even today, anybody here ever see one of these? How do you spell BlackBerry? Guess what? Radio front ends are ours. We economically enable them. Don't fall in love with technology alone. It's very important. Keep in mind that if the gold plating is thick enough, it'll never sell and never become impactful in society. This is what I mean about smarter planet. You got to be smarter, right? If you have essentially something that's going to cost thousands of times more than anybody's willing to pay, it's probably not smart to pursue it. There are lots of things we work on in this business. This is the laundry list of those things, but they've got to fit within a financial envelope that they actually get into society, because nobody can afford, in a place where you're having trouble living on $2 a week average earnings per capita, they're not going to be able to afford a sensor that helps prevent them from becoming ill from spoiled food if the sensor costs $100. If the sensor costs 1 cent, and you can lay this chemical sensor strip on top of the meat that you have in your kitchen, and if it turns purple, throw it away. That's great. People will do that. So again, you just got to keep in mind it's got to work in many, many ways, not just physically. Now, the track record in this industry, and here's the good news, is amazing. Now, people love numbers, billion, million, trillion. This is great. What all it says is for the same amount of money, you now can buy about 1 billion times as many computations as you used to be able to buy in the year 1900. But I don't really think, I don't like this particular version of how far we've come and why I have such faith that we will solve these problems. I got a better example in my view anyway, which is I'm about 6'2". If in 1956 I was standing in front of my house and I'm that height, and I simply grew in height at the same rate that computer systems grew in their ability to crank away, how tall would I be today? And the answer is, if I were to look down at present day, I would see the moon wrap around the Earth and smack me in the ankles. Real numbers, by the way. That's it's really, by the way, really simple math. Petabyte, kilobyte. Petaflop, kiloflop. Right? 10 to 15, 10 to the right, 10 to the 12th differential, 10 to the 12th, 5, never mind. You can do the math on that. And somebody's sitting over there doing it. No. The thumbs are working madly. In any case, here's a very interesting thing about why technology is such a challenge and why the world today we live in is so different. And it really is different. Those of you working in software, those of you working in systems, those of you working smart grid, all of those elements, there's a real focus on that because what happened to us in technology is this. We have twice taken technologies and scaled them to such a small dimension that the power went insane. The laws of scaling say that when you make things smaller, classical scaling, if you're going to put 1 million times as many things on the chip, which is Moore's law after 50 years, right? You put twice as much on the chip every year. After 50 years, you've now got 1 million times as much on the chip. So if you had a 1 square centimeter chip, you now have 1 million times as many things on your same 1 square centimeter. If you haven't done anything about the power, that would mean that if it was a 10-watt chip here, it's now a 10 million watt chip here, which in a laptop provides you with a brief but extraordinarily exciting experience when you turn it on. That's a problem. And what happened is, the way we got to that problem is there was a recipe that said you make things smaller. If you follow this recipe, if you have twice as many things on the chip, each burns half as much. Twice in history, once for bipolar and once for CMOS, people violated those scaling rules with these huge bumps of power. And in fact, that chip up there at the very top was an Intel chip called Prescott, which got so out of control power-wise they had to terminate the entire program and start over again with a different design point. My point is, we have been counting on success where this would go on forever to the right, and you would announce new things with constant power, and because the laws of physics say you can't continue to make things smaller forever, basically that has now failed. Well, if you're not getting this massive performance that you're used to getting every new generation, you'll still get density. You can make things more dense, but they don't perform a lot better. You better find other means to do it, and people have. They've gone from just pushing transistors to pushing multi-core, adding things like embedded DRAMs. You have local storage of data right on the chip. Why is that? Because you waste ridiculous amounts of power getting data on and off the chip, so you want to cache on the chip. Why EDRAM versus what's called SRAM, which is usually how they store data on a chip? Because it's 400% more dense. All of these architectural tricks, they're not really just technical, they're architectural, are now coming into play, and there's a ton of software behind them to leverage them. Now, gigahertz is gone. There was this foot race. We were trained Pavlovian style. I actually know people crazy enough to have slept out in front of stores waiting for the first 100 megahertz processor. This is like a cheap thrill. I mean, I know, we sit here now going, you got to be kidding, right? There are people, okay, I know they need to get a life. I got that part. But aside from them being incorrigible nerds, the fact of the matter is that was a big deal because we'd been taught forever, Pavlovian style, things have to go faster. And that's how we get more speed out of a machine. The joke is clock frequency went down. If you look at the current chipsets from Intel, they're a lot slower than they used to be in terms of the clock frequency. They're using other tricks. And innovation has taken many forms. The other thing is, like I said, just making things smaller doesn't work anymore. The reason is really simple. If you make things small enough, you get down to atomic dimensions. And if you're planning on using nuclear fission to make the atom smaller, let me know so I can get far away. So, the thing that's happened is people have introduced new materials, not just a few. Before the 1990s, the base materials used in silicon technology are highlighted here. This is for left-handed people, that's for right, never mind. It's basically just aluminum for your metallurgy, silicon is your semiconductor, phosphorus and boron are respectively your N and P dopants, and then oxygen is for making your insulator. That's a piece of cake. And by the way, in the 90s, you're talking about the system being, the technology was like 40 years old at this point, and that's all people used. But it got a little harder. So through 2005, people had to get a little more clever. So then they added fluorine and chlorine and germanium and copper and titanium and silicides, and all of a sudden, you were adding all these new materials. You know why? Because you made the thing smaller, and it no longer was faster, better, cheaper. It actually got really hot, didn't go any faster, and threatened to set fire to the machine. So you had to invent all kinds of tricks now to get more performance out of the technology other than shrinking it. And then came post-2005. Now, I have the dubious honor of actually having announced in 2003 that you couldn't make things smaller anymore without doing all this because you'd set fire to the user. The reason that was dubious, in 2004, somebody showed up and actually put my face up on a slide like this with a big red circle and a bar across it and said, ban Bernie because he said the end of Moore's law is coming. Didn't quite say that. I said that the end of scaling would come. It did. So after 2005, a funny thing happened. You had to do a few other things to get performance. That's actually what's currently in use in technology today, by the way, the periodic table. And by the way, if people could figure out how to use plutonium without killing anyone, they'd probably go for it. The problem is that this has gotten incredibly difficult. Now, there are folks who still cling to this notion that we're going to do more of more, which is make things smaller, faster, better, cheaper. And that's a really nice theory, but the reality is it's very hard to do. So you're getting into now some really exotic transistors. The reason these are exotic is these guys are standing up vertically from the surface. For the last 50 years, transistors lay flat on the surface. The trouble is that if it lays flat on the surface, you can't do enough to the surface to get adequate performance once you get down below about 22 nanometers. So what's happening is people are actually looking at taking the transistor, literally standing a little thin fin of silicon off the surface so they can wrap a electrically controlling gate around it and pinch off the electrical current through it to cut down on leakage. I mean, these things are unimaginably complicated to build. Also, there are other devices we're looking at that are literally different than a standard transistor. This is a silicon nanowire. These little wires here are incredibly tiny. They're only about 5 nanometers, or 50 angstroms, or about 100 atoms across. And there, you actually put a gate around the device. It's like a tube. So you have a silicon conducting tube, oxide around it. You wrap a piece of metal around that, and you can turn the tube on and off. I mean, these, again, are very exotic devices. They do work, but you struggle to get them to work. This is very difficult, but you know what? You haven't got a lot of choice. There's some really fancy stuff where these are carbon nanotubes. I think some of you probably heard of those. This is a material actually called Buckminster fullerene. Anybody know why? Because Buckminster Fuller really liked this particular shape that carbon exists in, and in fact had built a whole series of geodesic domes and other things using that structure. So when it came up, somebody nailed that. That, by the way, has been around. Here's a useless fact. Do you know when this stuff was actually produced first? That's 1800. Yeah, about 1800. They didn't know what the heck it was. At the time, they thought it was like talcum powder. In the old theaters, they used to use arc lamps, where you took two pieces of carbon, you put them close together, ran a high current between them, and that arc gave off a tremendous amount of light, and that's how they illuminated the stages at the very early times when people were using electricity rather than just using natural gas or some other flame. The thing is, when you do that arc, the fuzz that you find at the bottom of that arc lamp, it's, by the way, Buckminster fullerene. So they didn't realize they could have almost won a Nobel Prize if they'd known what the heck it was. There's a lot of stories like that. You'd be surprised. In any case, the problem you get into is, at the end of the day, there are quantum mechanical limits to silicon, and you have to find other ways around this. This is one of the reasons why this field is getting tough. And this is one of the reasons why you guys have a tremendous opportunity to add value. Because I will tell you that carbon nanotube transistors and graphene transistors made out of a single plane of graphite, these were all really nice ideas which somewheres in the next 2 centuries will come to fruition. Right now it remains pretty much as it has been, which is the time it will be between when you're talking and when they'll be ready is a time constant of 20 years. Eventually it will stop being a constant, it will shrink to 0, I hope. But for the moment there's a huge amount of work here, and it's valuable work, and it has to be done because you have to solve these problems. But right now we don't have any of these alternatives to silicon available, and as therefore progress slows, we need people to be working in other fields. Another interesting thing, even if you can produce these huge amounts of data on a chip, shipping the data is another physical problem. Believe it or not, you can't get electrical signals on and off a modern chip fast enough. They're what they call I/O bound. So people are working on incredibly clever things where they actually stack chips in 3 dimensions, and the actual off-chip communications are based on photonics. This is sort of along the lines of cheating Mother Nature. You know, you're using wavelengths of light that are 10 times larger than some of the bends you want the light to make. That gets very exciting to direct it around those corners. But people have done it, and there are a lot of very interesting ways of doing it with evanescent waves and other things of that nature. Again, another point is when you get into doing these sort of very sophisticated tricks, you actually can push the field forward. But interestingly, this is not about just semiconductor technology now. This is an incredibly complicated data set where you have multiple processors, an entire plane of memory that's close coupled. You have photonics above it. Controlling this thing in a sensible fashion so you can actually leverage what may be 5 cores per chip or 6, 8 cores per chip times perhaps 50 chips in a block, accessing memory and even sharing that memory coherently among multiple chips. Good luck. This is a hugely complex thing, and it is coming quickly. We are reaching the point in the roadmap of technology where the demands on the hardware and software side will lead to what I call co-design exclusively. It already is being done. People co-design hardware and software to get the best result. But this will become not just something that's a nice to have, it will be something that you must have. And what I think you're going to start to see is departments that work in this field are actually going to coalesce. Because it is through the kind of co-design that you will get the benefit at the system level, which is all anybody cares about. There's a lot of work going on in optics, another field that really in silicon had very, very little place until quite recently. Now people are integrating on-chip optics for this very reason. You are I/O bound. You simply can't get data on and off the chip fast enough. And even if you could, it costs you too much power to do it. If you try to ship data any kind of distance, the RC time constants and the power that's burned in doing so become unbearable. Right now, some of the bigger chips we have, roughly speaking, half the power of the chip just goes into getting data on and off. 50% is doing nothing more than shipping data. You're not actually computing anything. Then there's the cost thing. Remember my warning at the beginning, beware what you hope for, it may be expensive. All this innovation that I've been describing, it doesn't come cheap. And again, it teaches you now have to innovate in other ways, one of which is how you work together. And the reason is this. That is an EUV system. This is basically the next generation of lithographic tool to shoot things that are down at the dimension of, let's say, 10 angstroms to 20 angstroms, somewhere in that range. You're going to get 10 to 20 nanometers, rather. You're going to get basically to the point you're using these kinds of litho tools. That tool, give or take, cost about $167 million, give or take a few million, round off error. The thing about it is, it looks a bit like, imagine the largest electromagnet you've ever seen. Imagine powering it up and walking through an automobile junkyard. That's pretty much what this thing looks like. But nonetheless, it cost $167 million. If you're going to do this kind of work, you also have to ask, can you sustain that cost? Now, the reason I'm telling you this, again, has to do with the fact that you have to sort of rethink where you're looking for value and adding value in this business. It turns out if you look at the rate of growth of total semiconductor investment in black, and then the rate of growth of the actual revenues in red, you will notice those two curves actually look like they're going to cross at some point. That's a really bad thing. What does that translate to? When I started in this business, there were 300 leading edge fabs in silicon working in the basics. Today there are 2. The place, anybody here know where the integrated circuit was invented? Or who invented the IC? There's that, yeah, exactly. Kilby. Jack Kilby invented it. And he invented it at Texas Instruments. Beg your pardon?
TI or Fairchild.
Right, I know, right. There's a religious debate which I'll stay out of, but you are correct. TI basically is where they have the, quote, Kilby Center, which no longer does any work in this field. Even Texas Instruments, which was sort of the last of the holdouts, gave up about 3 or 4 years ago, said, I'm out of here. It is remarkable, and it's because of the cost of staying in this. It is unimaginably large investments. Just to build a modern fab today is about a $5 billion single expense. One fab. So, the problem is, and I don't want to overstate this, just to do one generation of technology right now is something on the order of about $2.3 billion for the current generation. That's just the R&D. That doesn't actually get you a wafer. Or putting it another way, your first chip costs $2.3 billion. Beyond that, the chips get a lot cheaper per, but that initial one's a killer. So you have to actually figure out how you innovate. And innovation can actually be cultural. And strange as it may seem, you folks will exist in a different culture than I did. The culture I existed in, there were a bunch of yahoos. There was, I think it was Andy Grove. Who was it who said, no, it wasn't. It was the guy from National. Real Men Have Fabs. There was a book published. And I'll have to remember, I was attributing it to Andy Grove of Intel, but it wasn't. It was the guy who actually ran National Semiconductor. And it was an era of yahoos. Everybody could afford a fab, after all, so that's what you did. The idea of working with your neighbor, that was out of the question. I mean, collaboration, what are you kidding me? The whole point was to strangle them, not to work with them. It's a little different now. In fact, the world has turned completely upside down. Right now, Silicon Valley is relocated to New York, which is strange, but hard realities. When Texas Instrument exited, even Semitech, which is the US consortia working on advanced tech, moved back up into Albany, New York, where in fact we built a multi-billion-dollar leading-edge research center, not just development, but really are working all the way down to about the 10 nanometer level. That tool shown there was in fact at SUNY Albany, which has become a massive international site. And all the companies shown there from all over the world actually have their main research center in Albany now. Tokyo Electron Limited, which is located all over Japan as the second largest supplier of tools in the world, has actually shut down their Japan-based research centers and moved into, in fact, Albany. Samsung actually has their base research center and will be shipping their first actual technology at 32 nanometer based upon all the work done jointly in Albany. And in fact, what has happened is there's a whole series of large fabs where this thing is actually a full flow fab. It's not like IMEC in Europe where it's what they call a, where you do unit process, where you do an oxide, or it's an actual fab. You actually can build full chips. And this investment of multiple billions of dollars has had a profound impact because the way it began is all these companies looked at this and said, if we work individually, we're going to get killed. So why don't we form an alliance? And the alliance which was formed is about twice, we're roughly twice the size of Intel, a little larger than that actually, in terms of total investment. It's the largest single group of semiconductor folks. We don't run around in Albany with a little badge saying, I'm from Samsung, I'm from ST Microelectronics. That's nonsense. It's a single team. And we do what they call pre-competitive work, because that pre-competitive collaborative innovation, and it is really radical collaboration. These are people who will later kill each other in the market. We compete. But when you're pushing the laws of physics, you really do need to have this critical mass of incredibly bright people. And you learn to put aside who you are and actually work as a team. And it's had a profound impact because when that happened, all the other folks who supply this industry said, wow, they become adults. They actually collaborate openly. So what did they do? They showed up because it's an ecosystem, right? You've got it's the largest single group of people working in the field in the world. So I might as well show up because if I get approved in the process that they're going to develop, I own a piece of it. Then beyond that, you get a lot of people, in fact, who came in from the tooling and materials area. So it's not just the manufacturing and other work associated with manufacturing that came in. All the tools guys showed up, as well as a whole lot of the people who bring intellectual property in form of circuit design. So this is actually what is now in Albany. So what started out 8, 9 years ago as this little tiny, cut shop of, let's grow a film, has become this massive undertaking. It just grew exponentially. And it's here in the US. It's something that we basically do better than most folks, and we've been very, very lucky. And in fact, they now teach this at Harvard Business School as one of the entry-level courses. It's called Radical Collaboration. These are people who should more naturally beat the hell out of each other, who said, you know what? You're pushing the absolute limits of science and technology here, and why don't we just at least put aside our differences in pre-competitive work and get on with it? And there are people who could never get over themselves and participate in such a thing, and I believe it's their loss. Because what I found is, as smart as you may believe you are, there are other people out there who are smarter, and you're better off working with them than against them. It's really easy. One of the most interesting experiences in my career at IBM is IBM can be a rather humbling experience, because never underestimate the people you have in a company of 400,000 folks that's been around for 100 years. And I was sitting in a bar in Hursley, England. Sorry, we sit in pubs. We don't, we're IBMers. We don't go to bars. So I'm sitting in a pub in Hursley, England. We're about to go the next day, myself and 4 colleagues, and discuss what it's like to have a technical career in the company. And my 4 colleagues are sitting there. We're about 3/4 of the way through this. And I look around and I said, guys, no offense, but I don't really fit in with this bunch. I got to get out of here. And they looked at me like I had had a little too much to drink. And I pointed out that, fellas, I am the only person at this table who does not have a Nobel Prize. Yeah, that's a little, there's a level set. That's Gerhard Binnig. I knew I don't have to write high temperature superconductivity, scanning, tunneling, microscope. I mean, and by the way, these are the most normal. I mean, they're great scientists, but they're actually pretty normal human beings. Though Gerd is a little, but yeah. Gerd, when he won the Nobel Prize, he marches out of the building. There are literally hundreds of reporters, sound trucks, satellites, right? And they're standing there, and they have these huge bouquets of flowers, which is the tradition in Europe that they hand the winner. He walks out, and he's wearing his shorts and a T-shirt. He walks out the door, says, "I haven't got time for you guys. I got to go play a soccer match." Because, he can't let IBM. So he goes and he actually plays the game. So the first picture we have of him after he won the Nobel Prize is he's standing there clutching these flowers with blood running from his lips and from his shins, and it's great shot. So, but that's, it's the accurate portrayal of the guy. Now, we have all of these things that IT can do, but we sometimes underestimate how hard it is to do them or how much the demand is. This is also kind of level set. There are about 2 billion people on the web this year, and it's estimated to grow very, very rapidly to 4 billion within the next 3 or 4 years. So, gee whiz, 4 billion people, right? There'll be about 1.3 billion RFID tags as of about 6 years ago. Nowadays, there, however, are 33 billion. That's growing rapidly. However, where it gets really interesting is people get all excited about data that this generates, right? We'll have to store 10 times as much in a 5-year period from 2006 to this year, 10 times. Here's what they miss. The Internet of Things. The demands on what you have to build, what you have to handle, and the software and hardware you create go up 2,000-fold from the Internet of Things. See, we're sitting here thinking, wow, 4 billion people. How about 1 trillion things are connected to the Internet? That's pretty much now. And they all spew data. Those things exist all around you. You have thermal sensors in here. All of you working on smart grid, you understand that your dishwasher will ultimately say, hey, is there enough power for me to turn on now? Or should I wait 30 minutes? Then there's the photovoltaic supply outside that is querying another organization that maintains the weather forecast to see if it's going to be sunny in 2 hours. Because if it's going to be sunny in 2 hours, they're going to send something out saying, hey, wash your clothes 2 hours from now. All of that requires data, vast amounts of it. And it flies back and forth, and you're sitting there going, how do I keep up with this? So the demands on what we have to build in this industry, here's the quandary. I just finished telling you this stuff ain't getting better quickly. In fact, it's not getting better at all. The rate of progress in semiconductors, we are struggling. We are struggling. And then you compound that with the demands that are going through the roof. So good luck, guys. I retire. Have a nice day. No, not going to happen. So the way you do this is you really move way up the stack. We call it holistic design. The good news is you can get multiplicative benefit if you work the whole stack. If you go from atoms and molecules all the way out to the system architecture around the globe, you wouldn't believe the benefit you can get versus being, I make chips. I love it. There was a history, as you know, where I make a chip. Actually, you have to put a little sign on your computer that says, you see, I made the chip. Whoopee. Yeah, that's about 1/10 of 1% of the problem, right? The chip doesn't really run without any software. And oh, by the way, if the software is no use, if you haven't connected this to something else, and oh, by the way, there are no sensors out there, well, then this can't do anything. And oh, yeah, then you need actuators. And, this is just a little piece of the puzzle. But if you work holistically up and down, you can do some pretty amazing stuff. Now, there are some innovations we've made working A to Z that are kind of cute. This is one of them. It's called streams processing. So much data, as I said earlier, is being generated and flowing in. What do you do with it? Well, one of the things you want to do with it is you want to reduce that until you get to the point where there's a human that's being fed a consumable set of data. This is to some extent what Watson does. Watson is a snapshot, right? Well, Watson says that you ask it a question, and it takes this huge amount of potential input, but gets it down to the point that it presents you with an answer, or at least something it thinks is an answer with some odds on it. This is very effective if you think about what happens, for instance, I'll pick a random example, orange juice. Very sophisticated example, right? Orange juice. You're a company, Tropicana, you buy oranges and make orange juice. Why is this important? Because you want to monitor the New York Stock Exchange, all the filings with the various commissions, video news, weather data. Why? Because the hurricane that was going to make landfall in Mexico suddenly turns north and heads for the orange groves. You want to be the first company that has a system that says, hey, wait a minute, they're about to run down our orange supply with a hurricane. I strongly suggest we buy every orange we can get our hands on in Texas and other places right now, because it's going to get really expensive in about 3 minutes when somebody else figures out the weather forecast just changed and there ain't going to be any oranges. I mean, not rocket science, you think, but you got to do it in a microsecond. Good luck with that. This isn't data mining. This isn't where you collect the data and go back and say, hey, I've got no oranges. This is not a useful finding. That's kind of like, hey, I'm going to starve to death. Great. You want to be a little more proactive. That means you have to go back and do this on the fly. This is a dynamic process, and that's very, very powerful. So that, again, is another way using a whole host of tricks. This is decision engines, it's software, it's hardware, it's I/O. It's doing things on the fly instead of after the fact. Again, this is another level you can take this problem to in order to attack these grand issues. This is another one I like. So there's a hospital in Toronto. It's called Sick Kids. Please, I didn't choose the name. Every time I say that, people look at me like, you know, that is the name of the hospital, Sick Kids Hospital. It has a terrific reputation, particularly for dealing with preemies. The problem with a preemie is an interesting one. Premature infants, of course, when born, have very underdeveloped everything, including immune systems. Well, that's catastrophic because hospitals, unfortunately, are notorious for having infections that transmitted in the hospital. They're called nosocomial infections. Any infection you acquire in your hospital stay. The trouble with a preemie is they don't behave like an adult does when you get sick. When an adult becomes ill and you're going to get a cold, what happens? You start blowing your nose, you sneeze. That's your signal something is coming on. Your body is reacting to an infection. And it's sort of your early warning system as your body spools up and fights it. In a preemie, they don't have an early warning system. So what happens is the child becomes more and more infected, more and more septic, and then suddenly, and very suddenly, dies. The child crashes and dies because there's no early warning. It's not like they develop a fever. How are they going to develop a fever? They haven't got a significant immune system to have that reaction. They're not going to develop congestion. Their immune system hasn't spooled up. They just die. They become septic. They go into septic shock, and there's no recovering. You need to discover this problem as early as humanly possible, that there's an infection pending. So what they do, a child throws off 100, 200, 300 data points per second as to respiratory rate, heart rate, any kind of variations in any of the above, temperature, body weight, electroencephalograph activities, a huge number, blood gas, I mean, you name it, it's all monitored. What if you took all that data every second for months until the child either successfully, hopefully left the hospital or, God forbid, died? And what if you went back and then you compared, the child has died, you look at all that data and say, where was there a signal something's wrong? Because no alarm went off. The heart rate was right, the temperature was right, blood pressure, right until the child died. It turns out if you go back and look at this, again, the power of what I showed earlier, data mining and technology and sensors and all that taken together, the system solution now, is what they found was the child's heartbeat actually should be quite variable. Young preemies, their heart rate wanders all over the place. The bizarre part is, as they become infected, for whatever reason, the actual variance in the heart rate goes away, and the heartbeat becomes actually much more regular and pretty much in the center of the sweet spot of where it should be, which means no alarms are ever going to go off. Except that stabilization of the heartbeat is what signals that impending fatal infection. We can now, using this technique, when I say we, I mean the hospital, can pick this up 24 to 48 hours ahead of the best ICU nurse and treat 24 hours to 48 hours early, which is the difference between children living and dying. So what we do doesn't operate in a vacuum. It does not operate in a vacuum. I gave this talk in Israel last year after I gave that example in Israel after their New Year. And one of the CEOs that we had invited came up and hugged me and turned and said, look, my child died 3 weeks ago of nosocomial infection. This is good stuff, thank you. And he walked out, you sit there and you scratch your head. there's no good reaction to that other than that, what you do matters. Remember what I said at the beginning, keep your eyes open. This isn't what people set out to do when they invented streams processing, I promise you. It is what happened, and it is what's in use today. So pay attention. It's never necessarily a straight line from A to Z, right? There are times where this is not what they had in mind, but this is what came out of it, and it actually makes a huge difference. There are many ways you can use this stuff well. Another example is, what if you have a city and you know where everybody in the city is in their car? Interesting. Not whose car it is, but just there's a car here. There are this many cars going by this spot, and they're going at a certain speed. If you take the history of the city, just like following a child, you can predict 20 minutes from now, believe it or not, what things will look like. You can predict the number of cars that will be at that spot and the speed of those cars, because you have a lot of historical data. You can actually predict the future. You build a model. These are interesting curves. It looks like there's one. This set of curves is a 10-minute ahead forecast in blue of the automobile speed, and in black is what actually happens. So in other words, we draw the black line after the blue line. The blue is our prediction, drawn 10 minutes ahead of the event, and the black is what actually occurs. You will notice they just sit on top of each other. It is astounding how accurately you can predict this. Why does this matter? I'm not going to come back and tell you, by the way, 10 minutes from now you're going to be stuck in a traffic jam that doesn't exist. That's not the goal. The goal is the jam never happens. Why? Because if I look at the speed of cars, which is 10 minutes ahead here, and I see the blue line falls off a cliff, the first thing I do is I start to reduce the number of vehicles I allow to get to that spot in the city by adding just 2 or 3 seconds delay to the lights that move people towards that spot. Because it's overuse in a spot that causes congestion. And all you have to do many times is reduce the number of vehicles by a few percent, and the jam never happens. Proactive. Okay, this is a foundationally new way of thinking of the use of IT. We are changing the future. We're not just predicting it, we are changing it. And that's a pretty remarkable thing. Now, this is pretty much it. As a company and as a group of people working in this field, particularly the technologists, we work in all of these areas that impact all of those, quote, green things that I showed earlier, all of those grand challenges. Every one of these has a piece of it. So this was my lecture, as I said, challenging the entire technology industry to focus on doing, better things with what they produce. And so, I wrapped it up here. I said, look, innovation is now the only thing driving our industry. The straight line stuff doesn't work anymore. Consolidation and globalization of society, of our industry and everything else are just going to continue and become the norm. Systems will be the differentiators, period. This is what I've been showing all along. It is the system solutions that really change the world. It is not, wow, I got a gee whiz, faster transistor. Didn't change the world. Those days are becoming scarcer. It's not to say somebody won't invent a new transistor or gee whiz device that makes a big impact, but it is to say that's not going to be the big thing. And as an industry, and when I talk about an industry, I mean in the broadest sense, as an IT industry, we have a profound ability to change society, and we have demonstrated it time and time and time again. You haven't even seen the beginning of it. If people can ever get over the concept that if you run a pig backwards through through a grinder, yes, you get sausage. But if you take the sausage and run it backwards through the grinder, you do not get a pig. Okay? If people could ever get past that, which is another way of saying you can anonymize data, and it really is anonymous. If they could ever get over that, we could actually share medical records and actually do this kind of data mining and work and learn a lot more about healthcare. Okay, that, by the way, I stole shamelessly from a friend of mine, Jeff Jonas, who is sort of the wild man of IBM. We bought this guy's, we bought his company. Anybody see the movie 21? Right, this is about a bunch of guys who went down and ripped off the casinos using card counting. Yeah, guess who took them down? Jeff. Jeff is one of the best guys I've ever seen with stuff like that. But one of the things he also contributed was the part about running the sausage backward through the grinder and not getting a pig. One of the things that gets in our way is there are still issues in society we need to overcome about letting us use these techniques and use them in private for the benefit of society. But the fact of the matter is, you haven't seen anything yet, because some of the things we'd like to do have been blocked and will eventually open up with, I believe, profound consequences for society and us in general. So I'm going to stop there. Thank you, and a few minutes of questions if you want. Yeah.
I've got two questions.
Sure.
One is facetious. I, I think that isn't the challenge proving to people you actually have a grinder. The less facetious question is, one of the things that was not on your Smarter Planet overview slide is smarter education. Since we're sitting on the university campus, I'd be interested in your thoughts on that.
Yeah, I actually have a 40-page presentation on that, which is why I didn't put it there, because once I know that, once I get going on that, we're dead. Yeah, smarter education, oh boy. As an example, well, a simple example, starting at the base. Kids in New York, on average, carry around book bags that weigh 45 pounds, and the city, to my understanding, spends approximately $180 million a year to grind up a tree, soak it in toxic chemicals, dispose of those chemicals, flatten to paper, print on it, and then ship it to someplace. $180 million a year to do this, right? So we destroy a wonderful natural resource so some kid can have spinal problems. Excellent. Perhaps we want to, electronic delivery of material. We're not talking rocket science, we're talking Kindle. And that's about as far from rocket science as you're going to get. But believe it or not, it's that simple, that crude at this stage in terms of moving to smarter education. It's amazing. I wish I could say, I would love to say something profound about cross-training and forget that. We're carrying around 45 pounds of books as a 9-year-old child. We sometimes lose sight of the easy stuff because it's cheaper and simpler. So that's a great question. But there's a much more.
Discussion later.
Yeah, there's much more to it beyond that. I'm not minimizing it at all. Quite the opposite. It's sort of a favorite topic. But there's a huge amount to be done, to be frank. There's a vast amount of stuff that can be done there.
Thanks.
Yeah. Yes?
If I could build on that question. So talking about smart education, I guess what I would imagine that as is what do you think that students in grad school or undergrad here at CMU or other universities should be studying or should be looking to do in order to be better positioned to contribute to system-wide innovation the way you're describing?
Well, okay, so I'm not going to use graphics. I actually, like I said, I really do have a 40-page pitch on this, but one of the first things you do is you have to become what we call T-shaped. What I mean by T-shaped is, for instance, if you have a tremendous depth in one technical field, you still should be able to have an intelligent conversation with your neighbor. Mind you, I've worked with many people who could not have an intelligent conversation with their doorknob. The fact of the matter is they became so narrow that they had literally, if you had, a Venn diagram, there's usually some overlap, no overlap. That's not smarter education. My own experience when I was educated, I'm a solid state physicist. I graduated and I could actually show you why there's a band structure in hydromorphous materials, which is kind of a bizarre and esoteric thing. The fact of the matter is, if you ask me anything about business or the things I had to work on, I had no clue. So I was forced to go get that education by literally following a guy doggedly around the world as he went and did deals and learning on the fly. Not the most efficient way to do this. The fact is, you have each other. And the most powerful thing about being at a broad-based university like CMU is you have each other. Learn from each other. It's when you go out at night over the beers, do me a big favor, actually talk about what you do for a living. Because what you'll find is the ability to have that intelligent conversation means that even if you don't know the answer, you will know who to go and ask for the answer. That is an incredibly powerful statement and a tremendous twist from being highly siloed. I am the world's expert on quantum chromodynamics, but I basically given a light bulb, a battery, and 2 pieces of wires, I'd be sitting in the dark. I actually had somebody, by the way, come from a major university, which will remain nameless and shameless, who actually showed up, and I gave this guy, I swear to God, a battery, 2 wires, and a bell, and he sat in silence. I was astonished, and the truth is, he just never, So my point is, the number one thing is leverage one another. You are a very diverse group. Your faculty are extremely diverse and the best of the best. Make use of that. That's the one first piece. That is the way you will be best prepared, because when you talk to somebody, they will not go down a rat hole of whether you know what a left-handed lepton is. They will actually also want to know whether you could also have an intelligent discussion about a smarter power grid, or do you understand the concept of using computational biology to try to preclude a disaster with a variant on H1N1. And you should be able to have a moderately, intelligent discussion on that broad set of topics. Do not narrow your. That is the number one thing. There are like 100 others, but right there is a incredibly important part of the preparation is becoming well-rounded. Okay. That was easy. That's one, softball. That's it.
Thank you very much.
Thank you.